Okay, so now we're finally at the topic of guaranteed learning of latent variable model through tensor methods. This is actually a tutorial I made in 2018, but I added some more content to it. Oh, what's going on? Should I? Okay. All right, so what are we going to cover, right? We will be mostly focusing on latent variable models. I'll motivate first why latent variables are important. Then after that, we will be mostly focusing on learning algorithms for latent variable models. So, we've learned about graphical model learning. So it's learning the graphical model, and latent variable models are indeed a subclass of the undirected graphical models we've learned. And the major mechanism or the major techniques I'm going to introduce is called the method of moments. But the method of moments involves doing some decompositions of moment tensors. Well, so that's why we will introduce the tensors, introduce what's a moment tensor, or also introduce what's a decomposition of the tensor. So to answer the question, thank you, David, for providing the link. They are linked at the end of the last time's slideshow. So probably I should also upload it to the website, just not to confuse people. Okay. So this slide is a illustration of what is going on here. So we have unlabeled data, right? So this unlabeled data are something that, some data without labels, right? For example, you have text. Let's say you wanted to categorize text. So, you just have the documents or articles. You could also assume that you observe some kind of social networks, right? So then you only observe the friendship network, but you don't necessarily get to observe why there is a friendship. What are the commonalities between these social actors that caused an edge between these social actors, right? So basically these are some unlabeled data, and based on some domain knowledge, we propose some kind of latent variable model on top of it. So now linking this back to the statistical learning theory, what this means is that we propose some kind of hypothesis class, right? So this hypothesis class becomes the latent variable model we choose. For example, you can think about mixture of Gaussian, you can think about, so latent duration allocation and other models. So this is some model that you choose, very much like a neural network you choose for your learning. So this is a certain model you choose for your learning from the unlabeled data. Okay, so this is your hypothesis class, capital H. Now, based on that, of course, you wanted to learn the small h within capital H. So the small hypothesis that best describes the underlying data, right? So that's like learning a hypothesis from the hypothesis class. So you can use a tensor decomposition algorithm to do that. So once you do that, you will learn a model. What is the model? The model is essentially the parameters that describe this latent variable model. Okay, we haven't seen any of them yet, but if you go back to think about, the graphical model scenario, then are these thetas that are describing the joint distribution of this graphical model. So that's, the model parameter. Okay, but in practice, the latent variable models have more structure. So therefore, the number of parameters they need to completely characterize the latent variable models is much smaller for a general graphical model, right? So in the worst scenario for a general graphical model, you would need exponential in terms of the dimension number of parameters to describe it. But in these latent variable models, you don't. That's why it is much more efficient to learn these latent variable models. So what does this mean? This means that you're simplifying your capital H. You're simplifying your hypothesis set H, hoping that you can have efficient algorithms. Does that make sense? So hopefully this is a nice link to the statistical learning theory, also linking back to what we learned last time about graphical models. Okay, so overall, the takeaway message is that latent variable model is a special case of these graphical models with some kind of structure that we enforce. Okay, so with this structure, the model, the hypothesis class becomes simpler, and therefore you can have more tractable algorithms to learn these models. Of course, the argument here is that although it's simpler, it still is rich enough to learn the structure from the data, right? So to characterize the data. So hopefully that's something, of course, we don't have a theory to guarantee that, but hopefully that's something we can make an assumption. Okay, so we have the tensor decomposition. Again, we haven't introduced it yet, but that's some algorithm we can use. And in the end, we're going to learn the model parameters, which is the hypothesis, small h. And then with this, model parameter, you can do inference, right? We'll learn about graphical model inference. It's like when you know the theta, when you know that, the joint probability of the graphical model, what are you going to do? So in analogy to supervised learning, this is like a prediction, right? So once you know the neural network, you have a new data coming in, you do the prediction, you get an outcome, and that's it. So similarly here, once you've learned the graphical model, or specifically the latent variable model, the joint distribution, then you're able to make predictions or do inference. Okay, hope this is clear. So the learning algorithm, as I emphasized, mostly, trying to emphasize is, the learning algorithms are trying to learn the parameters, so-called the parameter estimation. So you're trying to learn the parameters that describe the graphical model. So therefore, effectively, you're trying to learn the graphical model. So here are, I don't know. Okay, here are some applications. How do I get rid of this header here? Do you think that's fine? Don't know how to get rid of the header. Oh, there we go. Right, so I'm going to show a few applications where such latent variable modeling learning could be useful, right? So one example is the clustering, that you have this basic operation of grouping data points. Well, the hypothesis is that each data point belongs to an unknown group, right? So that's the most basic one, everyone's familiar with it. But if you do it from a probabilistic point of view, or you wanted to say from a latent variable point of view, latent variable model, I have a short, this is not necessarily the most precise way of describing it. I should say latent variable model instead of latent variable. So probabilistic view or latent variable model view, then the groups represent different distributions. For example, you have the Gaussian distributions for each of the subpopulation, and each data point is drawn from one of these given distributions, right? So this, for example, could be a Gaussian mixture. However, this is some kind of underlying model you're making an assumption on, right? Not in practice, the data is not necessarily coming from actually a mixture of Gaussian. Okay. So another application is this topic modeling. Actually, this is going to be something very important for our lecture, because I'm going to use topic modeling as an example, because it's not too complicated, but it's not also too simple, right? So it is right the amount of complexity so that we can understand what are the, what are the subtleties that, we might miss when we learn these kind of learning of latent variable models, but we also don't go into unnecessary details. So that's, the example I deliberately choose. So the topic modeling will be discussed a lot in the lecture. So what is topic modeling? You have like document modeling, right? So basically you observe words in documents or corpus. But here, let's assume that I want to learn the topic. So, this article is talking about music. Another document is talking about politics. So, these are hidden topics. We assume there is no label associated with these documents, but you want to learn these labels, right? So the goal is to do document summarization, right? So also this is a very relevant application using, that you can use latent variable models to solve it. So this is not only related to topic model. You could imagine expanding this to many different scenarios. For example, you have emails. So let's say you have emails from a company's employees and you somehow wanted to learn some information from those emails. So that's, again, not effectively. So, the data is not effectively really documents, but each email could be thought of as a document, right? So of course, there were other extensions even to computational biology and healthcare analytics and so on, right? So overall, I just wanted to say this topic modeling has a lot of applications, even outside of the actual, document summarization. So another application is to understand human communities. This is related to like social networks or any graph data that you observe the graph connectivity. So the graph connectivity means you have the nodes, you have the edges, but based on the observation, you wanted to understand the groups of social actors or commonalities of the social actors. By social actors, I just mean a node in a graph, right? So that's also highly relevant to these latent variable models. So yet another application is the recommender system. It is actually, I can think of it as a special case of the social network, but since it's drastically different in terms of the edge, because in social networks, the edge is just, whether we're friends or not, whether there is a connection between the nodes or not. But here, the nodes could be very different. It could be a rating of the user for various products, right? So not only I write a review for this business, so that means I have a connection with that business. As a user, I have a connection with that business, but I also have a rating associated with it, right? So I might rate it high or I might rate it low. So there is a number, but more importantly, I might even write review text associated with it, right? So, not only my edge is represented through a number, but it's also represented through a sequence of text, right? So that becomes more complicated, but that still falls into the, the regime of the, using latent variable models solving these problems. Okay, so this other application is the feature learning, learning good features or representations for classification tasks. Again, this is, I'm not going into the details here. So like I said earlier, there is this computational biology extension, so which is very similar to a topic model again, but of course, the terminology now is changed to computational biology terminologies such as gene expression levels, right? Instead of documents, you're observing gene expression levels. Instead of trying to discover topics, you're trying to discover gene groups and so on, okay? So yet another application is to the human disease hierarchy. This is actually some previous work from my group, but yeah, I don't want it to go too much into detail here. So how to model hidden effects, right? So basic approach can think about mixtures or clusters right? So hidden variable, you have this hidden variable H that is categorical. So for example, this H denotes the color here. So it's green, pink, and blue, right? So, but more advanced ways are using these probabilistic models. So it's not just a categorical variable, like, either this is blue or this is, pink or this is green. It's just a probability. Maybe with some probability, this point is coming from pink, or with another probability, this point is coming from green, and so on, right? So with this probabilistic model, hidden variables can have more general distributions, and can also model kind of mixed memberships, right? So it doesn't have to be either black or white, it could be gray, right? So this talk is the basic mixture model and some advanced models. So before that, what are the challenges in learning, right? So we talked about the challenges in learning for general graphical models, but even for these, basic goal in these, mentioned applications, there is this interesting component of discovering kind of hidden structure in data. So what does that mean? It means that we know that there are some hidden structure in the data. And our model actually also models that hidden structure, right? For example, in text, you have the topics that are hidden. In social networks, you have the communities that are hidden. But discovering them is very difficult, and you don't have labels. So you can only discover them through unsupervised learning. And as I said before, so you have this unlabeled data, and you throw a latent variable model on top of it. And this latent variable model would have some kind of latent variable intrinsically, right? For example, here, this is a latent variable. Now, with that latent variable model, you need some kind of learning algorithm. Was I signed out? Wait a second. Okay, so you need kind of learning algorithm to learn the latent variable models and then do the inference. So the challenge here is really some kind of conditions for identifiability. What do I mean by that? So it means basically what I mean by identifiability is that whether the model can be identified given infinite computation and data. So yeah, this is actually a very interesting concept in understanding learning in graphical models, or learning, or even learning any models, right? So if you are given infinite amount of data, and in supervised learning, it is hard to imagine that models are not identifiable. If you are given infinite amount of data and you're given infinite amount of computation, right? You should be able to identify a model within your model class. But unfortunately, this is not necessarily true when you have hidden variables. So because you don't get to observe them, therefore you cannot just enumerate all the observations. You can't. You have to learn something, and sometimes what you learn is just not identifiable. You cannot uniquely identify the model, even with infinite amount of computation or infinite amount of data, right? So that's something that's very different from a supervised learning or from some learning without hidden variable models. Okay, so that's one challenge, I would say, for when you have hidden variables. Now, also another challenge is, are there tractable algorithms under identifiability? So let's say even I know that the model is identifiable. Can you give me an efficient algorithm? Can your algorithm does not scale exponentially in terms of dimension, right? We are living, we're really looking at a high dimensional scenario because all data have a very high dimensional attributes, right? Many attributes. So basically the data lies in a very high dimensional space. Okay. So those are the challenges, essentially. Now, I talked about the challenges for conditions for identifiability, but even under identifiability, then the challenge is the efficient learning of latent variable models, right? So how can you design efficient algorithms for learning these latent variable models? So, everyone is familiar with MCMC, Markov chain Monte Carlo. It's a sampling method. It's a random sampling method. It is guaranteed to converge in most scenarios. So that's very nice. And that's why in application, people have been using that a lot. But unfortunately, if you consider theoretical guarantees, it is rather slow because of this exponential mixing time. Okay, so we know that for sampling, you do need to have a mixing time. And however, we cannot prove in theory that the mixing time could be efficient. Basically we can only prove like an exponential mixing time. So that is really bad. That doesn't qualify as a efficient learning algorithm for latent variable models. Now, what about likelihood methods, right? Everyone, has learned likelihoods, and variational inference is indeed using a lower bound of the likelihood methods for learning latent variable models. If you have learned about latent dirichlet allocation, there is this famous paper using variational inference methods to learn latent dirichlet allocation using a lower bound of the likelihood. So the problem with that is really, although the method seems to be simple, and using an iterative method, you oftentimes in practice it works very well. But the likelihood method depends on optimizing over the likelihood, right? But the problem with the likelihood is that it's non-convex and usually is not scalable, especially computing this likelihood is very expensive in a high dimensional space, right? Even the lower bound, also we're trying to optimizing over a lower bound and we do not have control over the lower bound either. So what's more, what's more concerning is that if you have a non-convex function, then you could have exponential many critical points. Again, by exponential, I mean exponential in terms of dimension. Could have exponential many critical points. And the difficult thing is that some of these critical points could be bad. For example, if you're trying to minimize or if you're trying to maximize the likelihood, these 2 points might be good. And maybe this one is not so good because it's a local optimal versus this is a global optimal. But you could also end up in these little valleys and you look at this peak and think that you already reached an output, a maximal point. But indeed, this is again a local optimal, right? So even you could have some kind of saddle points where, from one direction you're at a minimum and from another direction you're at a maximum and your gradient is still 0. So you still, you're still a critical point, but it is not a optimal solution, right? So because of this exponential many critical points, likelihood methods, again, although can be efficient, but the learning is with no guarantee, okay? So basically to summarize, MCMC could be guaranteed, but is slow, and likelihood methods is, not guaranteed, but could be fast in practice, right? Although my learning is not necessarily good. So what should we do? So essentially, the question is, can we achieve efficiency in terms of computation as well as sample complexity, right? So the answer is yes, we can find a good algorithm based on spectral methods. So the spectral method algorithm can achieve guaranteed learning and can be also efficient in terms of computation and sample complexity. Okay, so that's my motivation. It's kind of long, but finally I'm motivated why we are interested in learning these spectral methods. And indeed, that's a major topic of my group's research. So what would this tutorial cover? We will first use a motivating example to show why maximum likelihood estimation could be challenged for Gaussian mixtures. Even learning Gaussian mixtures seems to be a simple thing to do, but maximum likelihood estimators do not necessarily always succeed. And now, using that, we will introduce the method moments and tensor notations. So I'll introduce a few, tensor notations. Also, yeah, we should also share a paper by a CODA's tensor review paper where the tensor notations are well explained. So in case some of you are very interested in doing research related to tensor, I'll share that paper later on after class. So after that, we're going to use topic model as an example, especially wanted to use a simplified version of the topic model for specifically a single topic model. I will explain what that is. As an example to show how we can use method moments and tensor methods to solve model learning in topic modeling. We'll talk about identifiability. We'll also talk about parameter recovery using decomposition of the exact moments. Okay, so finally, after all that, I will make an argument saying, although learning latent variable models could be very complicated, but they could all reduce this to doing tensor decomposition. So, we'll make that argument. Now you don't see why, but hopefully I'll make that clear after that. Then our focus will be switched to the tensor decomposition. So I'll introduce some kind of algorithm, error-tolerant algorithms for tensor decomposition. The error tolerance is very important because in practice, the data is noisy. So we want to make sure that even under some noise, we could still recover the model correctly. And within that, we will have decompositions for tensors with linear independent components, also have decomposition for tensors with orthogonal components. Okay. So finally, if we do have time, I would like to introduce our project on neural network compression using kind of tensorized neural networks. I don't know if we will be able to cover that, depends on our progress. But if we don't have time to cover it in details, I will at least give you some ideas or high-level introductions to that. And then finally, we'll conclude. Okay, so this is an outline of what we will be covering for the next few lectures. Okay, so let's first go to the motivation. So any questions before I proceed? Okay, so let's see the motivation. We're going to look at the Gaussian mixture model. Indeed, we're going to look at a generative model. So for those of you who heard about generative model, if you started machine learning, after maybe 2018, you started to learn machine learning after 2018, then whenever you think about a generative model, you might be thinking about GANs, generative adversarial networks, or maybe VAEs, right? But so generative models are essentially just a data generation process. It doesn't have to be nonlinear. It could be nonlinear, and people prefer nonlinear generative models in terms of expressive power. But I'm going to introduce some kind of more classical generative models because that's easier for us to understand what are really generative models. So once you understand these generative models, the more advanced one, which is imposing some kind of nonlinearity on top of this linear transformations, could be better. Although that seems to be hard to characterize mathematically, but hopefully by learning these more simple models, you will be able to understand them better. Okay, so let's look at the more simplified versions of these generative models. Indeed, this is so-called the generalized linear models, right? So samples, so specifically I'm talking about mixture of Gaussians. The samples are comprised of k different Gaussians according to this categorical variable. So the categorical variable will take values from 1 to k. So you have k such groups, and each of them are going to occur with probability pi I. Okay, so the pi I plus pi k is gonna sum up to 1. And essentially this pi I just means the probability that sampling 1 point from the distribution with pi I probability, it will be from group I. Okay, so this is just a categorical distribution. I hope that's clear. And this is very important. If you do have a question, please ask that now, because we will be using this a lot in the later analysis. So I wanted to emphasize that now I should say example. So examples are comprised of k different Gaussian according to the categorical distribution, and each example is from one of the k Gaussians. Okay, so what I mean by that is, for example, you have in this picture, you have 3 different Gaussians, right? So each example, so if I choose this one, then this is generated from the green Gaussian. If I choose this one, it's generated from the blue Gaussian, or if I choose this one, it's generated from the pink Gaussian, right? So each example is from one of the k Gaussians, and each of them is characterized by this Gaussian distribution. So it's mu h and sigma h. So mu h is the mean of that specific Gaussian subpopulation. So mu1, sorry, let me just say mu green. So mu green is just the mean of the green Gaussian, and mu pink is just the, mean of the pink Gaussian. Of course, I'm not using green, pink, or blue here. I'm just using an index to denote which subpopulation this is from. Okay, and similarly, this is for just the covariance matrix for that Gaussian. And this Gaussian is a multivariant Gaussian because your data is lying in a high dimensional space. So if the data lies in a d-dimensional space, then it's a d multivariant Gaussian. Okay. So overall, this is the data generative process. You first generate the hidden variable, although you don't get to observe them in practice. But if you imagine such a data generation process, you are going to first generate a hidden variable, which is indicating whether this point is going to be green, pink, or blue. Okay, so once I do that, I generate that from a categorical distribution, then I can just generate my real example. So this is my real example that I'm generating, conditioned on what color I am, right? Whether I'm pink, whether I'm green, or whether I'm blue. So conditional on this color, then I can just generate my example based on the Gaussian distribution. Okay, so this is so-called the generative model. I'm just using this 2-step to generate each data example, and I can repeatedly do that for m times to get m examples.
I have a question.
Go ahead.
So in this example, the color is concretely the hidden variable h, but isn't it oftentimes that we can't observe h? So
we cannot. Yeah, that's the point.
Okay.
It is hidden. So I'm just trying to show you the generative process. So, it's very important to see the difference between a generative process and what you can observe in practice. The generative process is something that is not observed by a machine learning learner, right?
Mhm.
The machine learning learner would only observe this thing, what I'm showing here. So it's a bunch of dots, right? That's what you observe.
Will we ever know the size of h? Or is that kind of
usually in practice you don't know, but we may do a so-called model tuning. So what I mean by that is, you can think of that h, the K as the hyperparameter. The capital K is the hyperparameter. So, in this scenario here, so that's a very good question, but let me finish the slide and that question becomes more clear. So in practice, so this is just what, I mean by a data generating process. Apparently that is not something we will know. And essentially, if we know it, then the learning becomes trivial, right? The whole point is that we want to learn this data generating process or the generated model. But in practice, what do we do? In practice, the learning problem becomes that you have a bunch of data examples, right? So this is the data example. This is the training data set, right? You don't get to see their categories, of course. So you don't know their colors, but you only know, you can observe them in the vector space. So in practice, you would have this tabular data, right? Each data point is just one dot in a vector space. Even in images, you could also consider that, but it's just like a very huge space, very, very high dimensional space. So nonetheless, right? So you get all these data points. These are your training data set. This is your training data sample. Now you're trying to learn the mean vector, mu h, the covariance matrices, sigma h, for all h from 1 to k, and a mixing weight. So now the question, Laura had a very interesting question, right? An important question. So I don't know k, what should I do? So in practice, if you have a Bayesian approach, then you could probably estimate the posterior of that. But now if we don't take a full Bayesian approach, then we could just tune models. We could think of h as a hyperparameter. So we could train a bunch of models with different the k. I keep saying h. What I mean, the number of subpopulations. So I could just use that as my hyperparameter. I could just train, different models with different hyperparameters, and then I can just, do model selection from them, right? But for the simplicity of today's lecture, let's assume that I give you the true answer for capital K. So you know the number of subpopulations here. So even if you know that, that seems to be a simplified version of the learning problem. But if you think about it, it's not so simple, right? Estimating mean vector mu h, covariance matrices sigma h, and mixing weight, it is not so simple, right? Because to do that, you have to confidently estimate for every data point, what is its color, right? And then based on that, you will do estimations of these mean vectors and covariance matrices for each subpopulation. Okay, is this clear? Of course, I'm just laying out the learning problem yet. Of course, we don't know how to solve it yet. Okay, wonderful. Now, as I said, I'm going to use a motivating example to show why maximum likelihood estimator could not necessarily solve this latent variable learning problem. So let's just recall, in the maximum likelihood estimator terminology, basically you have your data, xi, I from 1 to n. Now, somehow I'm switching the notation for small n being the number of training examples in your data set. But yeah, but before we're using small m, but now we'll use and hope that doesn't confuse you. So now we have the likelihood of the data. Likelihood of the data is some kind of probability of the data conditioned on the theta. So it's just because the data examples are usually assumed to be IID, so it becomes just the product of the likelihood of xi conditioned on theta. Okay. So the model parameter estimation is just that you wanted to find the theta that maximize the likelihood, data likelihood. So that's just, the terminology of the maximum likelihood estimator. I hope everyone now has recalled your memory from your machine learning courses to recall what is the maximum likelihood estimator, MLE. So now the thing is that you have the latent variable models. So some variables are hidden. Therefore, you have no direct estimators when some variables are hidden. And how do you do that, right? How do you estimate the likelihood then? So people have been using some kind of local estimation, such as like EM algorithms. But I'm not going to introduce that today. But the point is, MLE for Gaussian mixture models is solving MLE estimator is NP hard. So here is a more detailed illustration of how do you solve MLE for Gaussian mixture model. So given data xi from 1 to n, the number of Gaussian components k. So now you're in a simplified scenario that you even know k, you even know capital K. Then the model parameters to be estimated are these ones. So it's the collection of this mu h, sigma h, and pi h. Notice that pi h is the mixing weight for that subpopulation. So you need to estimate that for all k components, right? For all capital K components. So if you write it out, for Gaussian mixture models, this is the MLE, this is the likelihood. So, if you wanted to learn the pi h, so of course this is conditioned on pi h, so this is the likelihood. What is the likelihood? So first of all, I'll explain this. This is probably not so obvious. So first of all, look at this part. So what is that? Can someone tell me what is this? What's in the box here? Gaussian? What Gaussian? So what is? I know this is a Gaussian, but what is it? Gaussian density. Yeah, multivariate Gaussian density, right? So this is the likelihood for a multivariate Gaussian. Okay, conditioned on that the model parameters are mu h and sigma h, right? Is that clear? So this is the likelihood of a multivariate Gaussian condition on that the model parameters are mu h and sigma h. So now, if that's clear, I'm going to erase it. Now, if that's clear, then what is this thing? What is this thing? So think about summation of do you see? So what's in this red box here is the summation of the pi h multiplied with my likelihood of the data conditioned on that the population is h, the subpopulation is h. Do you see? So what this is saying is the likelihood of the data that are within the subpopulation h. Does that make sense? So if that's the case, then you multiply that with pi h, and then you summing over all subpopulation groups. Then what is that? Can someone tell me from like the conditional distribution point of view? And so I'm gonna pause a little bit to see if people can understand this. Yeah, so the pi h's should sum up to 1. Those are the mixing weights. Those are the probability that, or the overall in expectation, the fraction of data examples that are in subpopulation H. Or you can say that it's the probability that a data point will be in subpopulation H. Yes. Right? So this is exactly correct, right? So, these are the conditional ones. This is the conditional probability. Now, if you summing over the conditional probability multiplied with the marginal distribution of what it's conditioned on, then what is it? First of all, without the summation, you multiply, the conditional probability with the pi h, the marginal of what's your condition on is what? It's a joint probability, right? So now with the joint probability, now you're summing over h. Then what is it? Yes, exactly. It's the PDF of the Gaussian mixture. It is also the likelihood. So let me erase it. How do I? So it is also the likelihood. Now this is the likelihood. Why cannot write? Right? And this is conditioned on, this likelihood is conditioned on the parameter. Sorry, this is. The parameter of the mixture of Gaussian is this one, mu h, sigma h, pi h. Right? Is that clear? Okay, so indeed, if you look at that, then you take a logarithm and summing over all the log likelihood, because your data points are independent. So you can just sum over the log likelihoods, which is basically multiplication of the likelihoods. And then you find the sigma that maximize them. Of course, the sigma is the collection of all the parameters for that Gaussian mixture. So this is exactly the reason why this is the MLE for Gaussian mixture model. Okay, hope this is clear. So the problem is that solving this equation is NP hard. I don't have time to cover or prove why it is NP hard, but these papers will tell you why it is NP hard. So solving the MOE estimator, even for Gaussian mixtures, is NP hard. Indeed, now I wanted to introduce the concept of consistent estimator. It is very important to understand that. So the definition of the consistent estimator is, suppose you have IID examples. Again, this is examples, not samples. Right? That are generated by distribution p theta xi, where the model parameter theta are unknown. Okay? So then this is exactly our learning problem. Okay? So now an estimator theta hat is consistent if the expectation, under expectation, theta hat and the underlying theta is close. So basically a difference of in terms of measured in terms of norm is 0. Of course, when you have enough number of examples. So this is a consistent estimator. I'm gonna pause again a second to give us some time to digest this, right? So this is the consistent estimator, meaning like your estimator theta hat will be exactly the model parameter if you have enough observations, right? So the theta hat depends on the n, right? Because how are you going to estimate theta hat, right? You're going to give the number of examples you observe, and you have a learning algorithm, use these examples to learn the theta hat. That's why, as n goes to infinity, this difference in expectation goes to 0. So what is this expectation over? Is that obvious? What is it over? It's over the randomness of the algorithm, and it's also over the distribution of the underlying data X. Okay, yeah. So it is not only the expectation over the distribution of X, but it's also expectation over the randomness of the algorithm. So sometimes your estimator is, your algorithm is a randomized algorithm. So you might get randomized results, but nonetheless, you would get an expectation for your randomized algorithm. And therefore, as long as the expectation would, be the same as your underlying model, then it is still a consistent estimator. So this expectation is very important here, especially for the random algorithms. So is this clear? Any questions?
Yeah, okay. I'm still confused about the randomness part. So it's the expectation over the randomness of the distribution plus the underlying distribution where X is from?
So the expectation is over the randomness. So you wanted to account for the randomness of the algorithm. You also wanted to account for the randomness of the underlying distribution of the data.
Okay.
Okay, so now once we know the consistent estimator, I'm going to tell you why even spherical Gaussian mixtures are so difficult to learn. So if you have enough number of examples, right? So hypothetically you observe infinite amount of data. Now, even if your Gaussian mixtures have identity covariances, so it basically means that this multivariate Gaussians have identity covariances. So if under that scenario, we can only prove that when K is 2 and pi h is 1/2. So the mixing weight is uniform. So, with half probability, you're from group 1 and half probability from group 2. We have only 2 groups. So under that scenario, under the spherical Gaussian mixture, meaning like for both subpopulation, the covariance matrix is just identity. So if that's the case, EM will be proven to be consistent. So as I go back to here, I'm saying you can use an EM algorithm. So you can use an EM algorithm to solve for this problem, right? So to solve for maximization of this quantity here. Okay, just to recall. So I'm saying if if under this very simplified scenario, you can prove that EM is consistent when K is 2 and pi h is 1/2. But if you have larger K, then you cannot prove that EM is consistent. It is very easily to trap in local maxima, and then your result could be far away from a global maxima. So it won't be consistent. So by looking at these papers, you will see that. Okay, so this is just to show, I guess my takeaway message basically is to show that EM algorithms will not work for a maximal likelihood estimator for Gaussian mixture. So this kind of motivates why we need to use spectral methods. Right? So practitioners often use EM with random restarts of course, this will take a long time to get near the global maximum, and it is intrinsically just inefficient. Random restarts just means that whenever you start your EM algorithm, you choose a random seed, a different random seed. So you ended up having very different initializations. And then, you could end up in different Bayesian of attraction for these non-convex functions. Okay. So hardness of the parameter estimation is indeed, is indeed exponentially difficult in terms of both computation and statistician. So it is statistically and computationally exponentially difficult to learn the model parameter, even under parametric setting. So, actually, these two papers are saying it actually requires at least 2 omega k running time, 2 power omega k running time, or 2 power omega k sample size. So this slide is just to show how difficult it is to do parameter estimation for mixture of Gaussian. So now I'm talking about how hard it is, but since it is NP-hard problem, so we cannot expect some efficient algorithms, right? So how do we get around it? So there are ways to get around it by making some assumptions to simplify the problem. So there is this first assumption of separation conditions. So it basically means that, relative to the variances of these Gaussians, the means are separate enough, right? So they are separate enough for us to, separate this two mixture of Gaussians. This is intuitive, right? Of course, when you're here, let me again. So of course, when you have the same variances, when the means are more far away, it's easier for you to identify the models. If they're closer, then it is unlikely. But of course, this difference between the mean conditional means also is a relative quantity, relative to the variances, right? If your data is more spread out, then it's harder for you to distinguish them. But if your data is more concentrated, then of course it's easier for you to distinguish these two Gaussians, right? So this is a very naive or like easy to understand kind of condition. It's called a separation condition. So assuming that this quantity is sufficiently large. And there are indeed some papers on that. Now, there are other kind of conditions, such as structural assumptions, right? So for example, we can assume that the data, somehow some sparsity. So sparsity in terms of, the sparsity in the covariance matrices or the sparsity in the data. Or there is also the separable kind of condition. So for example, the anchor words is kind of a separable condition on the Gaussian or the mixture of Gaussian model. So I don't want to give too much details here, but more importantly, I'm trying to introduce this condition, which is so-called a non-degenerate condition. This is the condition we'll be focusing on. And I'll claim that this is a relatively mild condition. What is the condition? This is assuming that the mu1 through mu k span a k-dimensional space. So what does this mean? This means that they are linearly independent, right? If they span a k-dimensional space, then mu I through mu k are linearly independent. If they're linearly dependent, they won't be able to span a k-dimensional space. If one of them is dependent of the other, then it's just k minus 1 or even smaller dimensional space, right? Is that clear? Right, so can someone recall what is that linear dependence? I hope we still remember what is linear independence. So linear independence just means that there doesn't exist such a mu I, such that mu I can be written as the summation of right? You cannot write mu I in terms of a linear combination of the other things. I forgot, do we need the alpha i's to sum up to 1 or something? I mean, can someone remind me? Sorry, this is J as well. No? Okay. Okay, so it's just that, right? Is this okay? So there shouldn't be such a scenario. Then they are linearly independent. Required to not all be 0. Yeah, sure. If they're all 0, then this will be a 0, right? This shouldn't, the mu s should in general just not 0, I guess. Yeah, okay. All right, so this is just a recall of the linear independence. Now this tutorial is trying to statistically and computationally efficient learning algorithms. So we'll introduce those algorithms for non-degenerate instances using method of moments. So I will motivate why this seems to be a mild condition, maybe using the topic model scenarios, but just keep in mind that now this non-degenerate condition is just that we don't allow them to be linearly dependent. We have to have linearly independent conditional means for this subpopulation. Okay. All right. So now we're finally done in terms of motivating why MLE is challenging even for learning Gaussian mixtures. So now I'm going to introduce the method of moments, and this is probably the most important slide from today's lecture, is to have a very conceptual introduction about what is method of moments. Even if you walk away out of today's lecture, don't remember any of the detailed methods we introduce, you should remember this idea of method of moments. Of course, I will also introduce some tensor notations. This will be helpful for our understanding of the later explanations, but really the concept of method moments is the most important thing from today's lecture. So this is essentially the most important slide that I was talking about. So method of moment at a glance, right? So what is a method of moments? I wanted to first focus on bullet point 1. Bullet point 1 is saying, if you wanted to determine function of model parameter estimatable from observable data. Okay, so that's your goal essentially, right? Thinking about the learning problem, trying to learn the model parameters theta from the observed data. So from your data observations, right? Your training data set without label. So essentially, because you have a model, you have an underlying model, this is a parameterized way, this is a parameterized approach. So you have hypothesis class H in mind. Therefore, you can write a closed form solution for moments. So this might be a little bit confusing at first. So I'm gonna ask you one question here. So instead of this, if I started with theta expectation over theta of x. So can someone tell me whether you're able to write it out in terms of in terms of the theta. So basically, some kind of function of theta. So what I'm saying is, can you have a closed form formula that you can write out for this expectation of over theta, expectation of x over theta? Once you know what is the latent variable model you use, for example, you use mixture of Gaussian. So you would, what I'm saying is, can you write this in terms of mu h, sigma h, pi h? Can you? Okay, so now if this is too complicated, I'm going to give us more simpler case. Let's say your x is just Gaussian. So your x is, I'm making the assumption of the Gaussian, so not Gaussian mixture, but just Gaussian. So can you write, I'm saying the Gaussian has mean mu and a covariance sigma, okay? So can you tell me what is expectation of x conditioned on theta? Can you write it out? Yes, right? It is just mu, correct? Although I don't know mu, but I can write it out in the closed form as a function of theta. Do you agree? Theta, of course, include the mu and the sigma. Okay, so now this is good. Any questions? No? This is very important. I want to make sure everyone gets this because this is the most important slide from today's lecture. Okay. So now I'm gonna make it a little bit more complicated. I will say this is from the mixture of Gaussian. Then what is my expectation of x? Right? This will be my expectation of x, right? This is a linear combination of the mu's with the probability mu h, pi h for the mixing of the mixing weights. Agree? Yeah. So, right? So what I'm really trying to say is, now let me erase everything. What am I really trying to say? I'm trying to say that for, so if you know the hypothesis class, so you know the latent variable model, you would know how to write a moment of this thing as a function of theta. That's what I mean. Now, is this clear? So of course, there is this caveat that I don't know what is f here. I gave you a simple example that f being identity, so this becomes expectation of x, right? But but if you know the model parameters, then even if f is some other things, as long as you know what f is, you should be able to write it out, right? Actually, in practice, f could be, for example, it could something like this. So f is just xx transpose, or even some kind of a third order kind of thing. So it would be something like this, but I haven't introduced the notation of that yet. Or it could be also like the example I showed before, expectation of x. Okay, so it depends on some model identifiability that I'll introduce later on. So the f here is just a mystery for now, okay? But I'm just showing you that some examples of f here. Right, so nonetheless, the most important message here is that this so-called moment could be written as a function of theta. Okay, so now that's that. I hope everyone has grasped the first bullet point. Now going to the second. So the second is saying that you can form some kind of empirical estimation of the moments using data, using your IID examples, xii from 1 to n. Okay, so is this clear? Now let me just say expectation of x. So can you tell me how you would evaluate it, right? Given the examples, it is nothing but just 1 over n, I from 1 to n, xi. Right? This is going to be my empirical mean. Of course, this will be expectation or the estimation of the expectation of x, right? So is this clear? Can you give me a thumbs up or thumbs down if that's unclear? Okay. Okay. Yeah, wonderful. I see a lot of thumbs up. I hope this is clear. So what I'm saying is now, with the actual moments, you have a function that is related. It's a closed form solution, not solution, a closed form formulation for the model parameter theta. And now with the empirical moment, you can use your data to get the empirical estimation. So now here comes the third step, which the most important step is the moment matching. So because based on concentration inequality, which is also what we learned at the beginning of the lecture, of the class, when n goes to infinity, these two quantities will be exactly the same. This is just concentration. We're not even using concentration bound. It's just the law of large numbers, maybe, or central limit theorem, something like that, right? So you know that this expectation will be the same as the empirical estimation when your data is it's infinite. You have infinite number of examples, right? So you're going to make this two to be equal. So now what happens in this scenario? So if you have this, okay, so if you have expectation of theta, now I'm choosing my f to be just identity. So I'm just saying, if I have that, right, this is just a special case of the equation above when f is just identity. So if I have that, and then also my data is just Gaussian. So basically I can just estimate my mu using, because my left-hand side is just mu, my right-hand side is just 1 over n. Okay, so what does this mean? This means that I can just learn my mu using infinite amount of data using the empirical mean. Okay, so then I learned my model parameter mu. It's one of these model parameters, right? So now what about the covariance? Can I also learn my covariance using my data? Yes. So as long as you have your fx to be something like xx transpose, you will, okay, so actually that's what I plan to do today. So as long as you have f to be something more complicated, not only the data itself, the expectation of the data itself, but the pairwise interaction of the data. So it's the covariance of the data. Then you should be able to learn the sigma, right? By some simple manipulation. Of course, you have like subtract the concentration and so on. But anyway, you will be use a more complicated f to learn the sigma for a Gaussian. And similarly, also for a mixture of Gaussian, you will be able to do that. Now the question is how complicated your f can be. So that's the end of today's lecture. Hopefully next time when we pick it up from here, we will see how we can extend this to a mixture of Gaussian, because Gaussian is too trivial. There's no hidden variable. And I wanted to emphasize that we don't have lecture next Tuesday because of election day. So I hope everyone can go and vote, but please stay safe. All right, thank you, everyone.
Thank you.
Thank you.